You get a call from the help desk. The guy on the other side of the line says there's something wrong with the .50 network. Servers are acting up and users are calling in and complaining. And right after that, Jason over in cybersecurity calls you and says that they're getting alerts on the .50 network. The alerts say port scanning, but it's not really specific. You tell Jason that you'll take a packet capture and get back to him and let him know what you find on that .50 network. Jason seems a little bit anxious and maybe even a little scared. It looks like this might be a real hacker and not a false alarm. So this is our basic network layout. We have 3 networks, a 192.168.2.0/24 network with an internet connection, and we also have a .50 network and a .100 network. We first get a packet capture of the 192.168.50.0/24 network. We take a full packet capture without filters because we don't know what is doing the scanning and what's being scanned. So what do we do now? I start scrolling through the packet capture and not really seeing anything. Have you ever had this happen in Wireshark? You're just kind of scrolling through packets, looking at the packets on the screen, but not really knowing what to do. This was my experience when I first started learning Wireshark. And yes, there's a lot to learn to it, but you can learn it. Learning Wireshark and networking takes time, but each time you learn something, you will get a bit better and you'll see things that other people cannot see. Then, the next thing you know, people are asking you to look at packet captures for them, and you're the expert. So we think about our signs of NMAP scans. Maybe we look for icmp timestamp requests. So we use a filter, icmp.type equals 13. Nope, nothing there. Should we look at pings? Let's try the filter icmp. Do we see many pings in a range of IPs? Nope, I only see 2 pings total. What about pings without responses? Nope, all of the pings that I see here have replies. So let's try something else. Okay, let's change our filter to tcp.flags.syn equals true. And then go to Statistics and Endpoints. After that, we'll click on the TCP tab and click on Packets 2 times, so we can sort by the largest number of packets per IP address and port. And be sure that Limit to Display Filter is checked. Now let's look at the top few lines of this table. These are the IP addresses that have the most send packets per port. What we're trying to find here is port reuse, which is our number 2 sign of NMAP scanning. Look at how many more packets are on this first row, which looks like an NMAP scan to me, versus how many packets are on the other rows, which look like normal conversations. So let's put the data from this first row into words and think of it another way. It's telling us that IP address 192.168.2.22 started 1,000 TCP 3-way handshakes using a single TCP port 62371. And that is a lot of reusing the same port. So let's select this top line, right-click on it, go to Apply as Filter, and select it. This changes the filter to the 2.22 IP and port 62371. We see that the host potentially being scanned is 192.168.50.240. So now let's change our filter to ip.addr 192.168.2.22 and ip.addr equals 192.168.50.240 so that we can get all the interaction between these 2 hosts. And let's run through our signs real quick to verify that this is a packet capture. Number 1, many pings or ARP requests. Not many this time, but we do see now where 192.168.2.22 was pinging 192.168.50.240 at the beginning of the scan. So our sign 1 is still good here, because as usual, the NMAP scan starts with either a ping or an ARP request. Number 2, source port reuse. Yep, 62371 gets reused over and over again. Sign 3, time. Well, let's see. We start at 233 seconds, and if we scroll down here, we finish at 253 seconds. So yes, 20 seconds to talk to 1,000 ports. It fits that sign too. What about sign 4, SYNAC retransmissions? Nope, not this time. I don't see any. Or sign 5, a single IP going to the same destination port on multiple hosts. Nope, I don't see that one either, since this is just one host scanning another host. So lastly, what about sign 6, TCP resets? Many TCP resets directed at a single IP from one or more hosts. Yep, I see that one here too. All of the red packets. So this is definitely an NMAP scan. And if we look at the destination ports, you can just see that NMAP is just counting down through the ports like it normally does, starting with 5900, 135, 995, 443, 1720, 25, and 199. That looks exactly like an NMAP scan. And look, here in just a few minutes, we found an NMAP scan and a packet capture of 20,000 packets. You ask the apps team what the 192.168.2.22 server is, and they say it was a test web server, but it should have been deleted a long time ago. Whenever you hear something like this, be afraid. Be very afraid. It's always the servers that you don't know about, the ones that don't get patched and that have vulnerabilities. Those are the ones that get you hacked. Now that we know that the Nmap scan is coming from this server, let's hop on over to the .2 network and see what's really going on. We update our network map with the server running Nmap here and our first scan victim here. Next, we will take a capture on the .2 network here where the Nmap scanner is currently running. Now let's take a look at the packet capture on this .2 network, and let's use another way to find the Nmap scans. We know that default Nmap scans will start with pings or ARPs. So let's put in the filter icmp.resp_not_found, or ARP. These are the IP addresses and a range of IPs that get scanned, but there's nothing there to reply. These unanswered pings are evidence of an Nmap scan. A range of consecutive IPs being pinged seems suspicious. I see a group of these between 50.225 to 50.231, and I also see another group at 50.241 to 50.246. So let's comment the first packet in each group. Right-click the packet and go to Packet Comments and then Add New Comment. On packet 9808, I'm going to add port scan started 50.224 to 50.231. Now I will do the same for the next range of IPs that I found, and I'll label it port scan started 50.241 through 50.247. And I'll do the same with two more ranges of pings that I found that have no response. All of these comments will act as a roadmap for us while we analyze the PCAP file. So now let's look at ARPs, just to see if there's another port scan here somewhere. As I'm scrolling through, all the ARPs look pretty normal up to packet 60123. Then what we see is 192.168.2.22, which we know is our port scanner, is sending out a lot of ARPs starting at .1 and then going all the way to .254 on the 192.168.2.0 network. Since we know that when one machine is counting through the whole network, sending out ARPs, looking for IPs that are out there, is part of a port scan, let's comment packet 60123. Port scan started 192.168.2.0/24. Since we know where our port scanner is from the last section, let's change our filter to ip.addr equals 192.168.2.22. Let's look at another way to see Nmap scans, but this time visually. We can see short bursts of traffic on a graph. I'll go to Statistics and I/O Graphs, and I'll also make sure all packets is unchecked and that filtered packets are checked. And again, this is everything coming from or going to 192.168.2.22, which we know is doing Nmap scans on our network. Notice the spikes on the graph. Since we're looking for a lot of packets and a short amount of times, these could be the Nmap scans. If you click on the peaks, Wireshark will move to these packets in our packet list. Let's click on a few and look. Based on the IP addresses that we commented on earlier and all the TCP resets, I can tell that these are our Nmap scans. If you would like to see a video on just using I/O graphs, let me know in the comments. Let's close I/O graphs and get back to our packet list, and put in a filter frame.comment. We highlight our first comment, packet number 9808, and add or ip.addr equals 192.168.2.22 to our filter, and hit enter. Notice that when we switch that filter, our commented packet from before is in the center of our packet list. And the reason why we're doing this is so we can see the packets right around that comment. On this screen, let's step back just a little bit and see what's going on. We see a lot of ping packets from 192.168.2.22 and no replies except one from 192.168.50.230. So let's comment this packet, number 9818, port scan of 192.168.50.230. And let's add on to the end of our filter and ip.addr equals 192.168.50.230 so we can see just what's going on between these two hosts. We see that 192.168.2.22 is targeting many destination ports, and it's reusing the same source port, tcp.56695. We see a lot of TCP resets, and time-wise, this happens from 138 seconds to 143 seconds. So 5 seconds for 1,000 ports. And we know that's way too many ports in a short amount of time to be normal user behavior. Now let's go back to our comments again by changing our filter to frame.comment. Select the packet 24041, where the second scan starts. Now we put in our filter for our scanner, or ip.addr equals 192.168.2.22, and now that commented packet is in the center of our packet list. We step back again and see a bunch of pings, but only one reply from 192.168.50.240. So let's comment on that one. Scan of 192.168.50.240. This 192.168.50.240 is the same target as the very first NMAP scan that we saw. This is the same exact scan, but our capture point is on the 192.168.2.0 network, where that old test web server is that's doing all the NMAP scanning. So let's change our filter back to frame.comments. For these next two comments, port scan started 4.240 to 4.247, and port scan started 5.241 to 5.247. We don't even need to go through those because we're going to add a seventh sign of port scanning. And this one is when networks that are being scanned are not our networks. See, we don't have a 192.168.4.0 or a 192.168.5.0 network. So for this seventh sign, for networks that are not ours, what it really shows is a hacker probing around or looking around for networks. Again, since users are going to mostly use DNS, they're not going to be finding or looking around for any networks that are not there. One caveat to remember when we're looking for port scanning in a capture is that this could always be our own network management or security server. These servers will do a lot of pings and scans. For the last section of this video, let's talk about command and control traffic. In simple terms, command and control, or C2, describes techniques that hackers use to issue commands to and control a compromised server. So in our case, who is controlling this old test web server that shouldn't even exist, that should have been turned off a long time ago? I am. What I'm thinking is that every time we see a scan start, we should see some C2 traffic telling that scan to start. So now let's look right before each scan starts and see if we can find this C2 traffic. Let's highlight our first commented packet, number 9808, and then put in our filter, or ip.addr equals 192.168.2.22. Since we know that's where our scans are coming from. Now that our commented packet is in the middle of the screen, what do we see right before that scan starts? I see there's an IP address that starts with 172.27. So now let's keep going and see if that's a regularly occurring IP address or if that's just some random IP address. Let's change our filter back to frame.comment so we can just see the comments again. We will skip over the second comment since it's a part of the first scan range and there should not be a command that directly caused it. So I click on the third comment and then change my filter to or ip.addr equals 192.168.2.22 again. There's the comment in the middle of the screen. And again, right before that comment, we do see the 172.27 address. So now let's go back to the comments and check again. So let's select packet 30595, and then I'll add or ip.addr equals 192.168.2.22 to the end of my filter again. And again, we see the IP address 172.27.72.127 right before the NMAP scan starts. So this is actually looking pretty promising for this being our scanner. So what I want to do next is add a filter that shows the 172 address and all of our comments. So that filter is frame.comment or ip.addr equals 172.27.72.127. So one thing that we can see here is that the first three packets in our packet list are the three-way handshake. We see a SYN, SYNAC, and ACK in those first three packets. So what I want to do here is show only data packets. So I'll just add to the end of my filter and tcp.payload to give me just those data packets. So let's click on one of these blue data packets and then right click and select follow and then TCP stream. What we have here is the data that the hacker is sending in blue and our server's response in red. We can see every command he sent and the results of every scan. In this case, the hacker has compromised our 192.168.2.22 test server, the one that should be down, and it looks like he sent some kind of reverse shell back to his IP at 172.27.72.127. Now this traffic could have been encrypted or using some kind of command and control software, and we might not be able to see the commands, but we should still be able to see the encrypted commands happening right before each of the scans start. Thanks for watching. If you're still watching at this point, then you're likely a subscriber, or maybe you should be. The next video will be a continuation of this series focusing on using Wireshark to find web hacking, or I may do a really good intro to networking video. I haven't decided yet. If you'd like to see one or the other first, let me know in the comments. I'd like to know what you think. And as always, I'll see you in the next video.